All right, so I think we did finish off talking about polar covalent bonds, and we just started them, right? We didn't really get into them and finish, I think. So, cast your mind back, think about a covalent bond, shared electrons. Again, we're looking at it more conceptually than what really happens in an atom. So we've got these pairs of electrons. For each covalent bond, there's a shared pair. And if it's between two atoms of the same or very similar electronegativities, then those negatively charged electrons kind of in the middle. So think about the bond as this line. So the electron's right in the middle, so one side of the bond is no more or less positive or negative than the other side. Is everyone okay with that? Kind of even across the bond. All right. A polar covalent bond is different. When the two atoms, and let's do, for example, an oxygen and a hydrogen, when the two atoms are of quite dissimilar electronegativities. All right. Oxygen, do you remember what that was on the electronegativity scale? About 3.5. And hydrogen?
Yeah, 2.1.
A 2.1. So, this one is a lot more electronegative. It exerts a much greater pull on the electrons outside of the atom. So the electrons are kind of pulled over to the oxygen side. Now, that generates polarity across that bond. This end of the molecule, or the bond, is sort of more negatively charged than this end. So can you see now why we've got the polarity? Yep. All right, a negativity side, a positivity side. That means that this oxygen side of the molecule is going to be slightly more negatively charged than the hydrogen side, which will be slightly more positively charged. Okay. What balances out the negative charge of electrons in an atom? The positively charged protons, right. Okay, so if the electrons are pulled away, what's left there is the proton, which is the nucleus, and that's where the positive part comes from. Oxygen still has a nucleus. The negative electrons over there sort of counteracts the positive charge of the nucleus and makes it more negatively charged. Everyone okay with that? All right. So, polar covalent bonds then. Good? It's really important you understand polar covalent bonds because we're going to be talking quite a lot about hydrogen bonding and water. And in order to understand hydrogen bonding and water, you've got to understand polar covalent bonds. So there's our water molecule. And you can see we've got our oxygen and our hydrogen in good old H2O. And you can see that there's a negative side to the water molecule around the oxygen and a positive side to the water molecule around the hydrogen. Now, we usually use this symbol to indicate a positive side or a negative side versus a full-blown negative or positive. When we put a negative or a positive by an atom, that usually says you have a negative charge or you have a positive charge. Right, this says you're kind of more negatively on that side. And this says you're kind of more positively on that side. Does that make sense? Yep. Okay. All right. Any questions about polar covalent bonds then?
So the electronegativity, is there a correlation between electronegativity and valence electrons? Or is it kind of just measured differently?
The more highly electronegative, the more highly
Isn't fluoride, isn't there like one?
Fluorine has an electronegativity of 4 on that electronegativity scale.
Okay.
So,
But like its valence electron number, isn't really, it doesn't come to play with the electronegativity?
no, it kind of does. So think about fluorine, chlorine, oxygen, and nitrogen. On the periodic table, they're all sort of clustered, aren't they, in that upper right corner. And so fluorine needs 1 more electron to fill it. Chlorine needs 1 more electron to fill it. Oxygen needs 2 more electrons to fill its valence shell. All right? So the reason why they're much more electronegative, again, I didn't really want to go into this, but since you asked it, no, it's fine. It's totally fine. So let's think about the nucleus on a fluorine atom. Fluorine's got an atomic number of 9. That means it's got 9 positive charges in the nucleus. And it's got 9 electrons. So how many shells does fluorine have? 2.
So that fuel first, and then we have 7 on the
And then 7. 1, 2, 3, 4, 5, 6, 7. All right. So one reason why this is so highly electronegative, in other words, it has a huge attraction for electrons outside of that outer shell. This is, for this distance, only got 2 shells, this is a dense, very positively charged nucleus with 9 protons. That 9 proton exerts its influence beyond the atom out here. Okay? Does that make sense? Chlorine is similar and oxygen is similar. All right? If we were to add just 2 more protons to this, we would have an atomic number of 11. Which element is that? Sodium. So we've only got 2 more protons, but we've added now another shell. That is a huge distance now for just 2 more protons. Massive distance. It can barely hold on to that electron in its outer shell. Very low electronegativity.
So is it trying to get rid of it?
Well, it loses it easily.
Okay.
And we'll get onto that. That's what we're going to talk about next.
Sorry.
It's all right. It's good questions. That's another interview tactic. If you're a bit flustered, a bit confused, ask a question. But get those questions like pre-figured out, so you can go in and put them in your little arsenal of stalling tactics. The other one is to take a drink, or ask for a drink, or just take a drink, and that sort of lets you regain your composure. All right. So water then has 2 polar covalent bonds. It gives the molecule polarity, and that polarity, explained by polar covalent bonds, gives water its unique properties. Water's got some very unique properties that we're going to talk about in much greater depth in a moment, but it's things like it's a very good solvent. Lots of things dissolve in water. Lots of things don't, but lots of things do. Sodium chloride dissolves in water. Carbon dioxide dissolves in water. Hydrogen chloride dissolves in water to form hydrochloric acid. Ammonia dissolves in water. Lots of things dissolve in water. It's a good solvent. It's the solvent of your body. It has something called cohesion, which means water molecules like to stick together. And it has something called adhesion, which means water molecules like to stick to a lot of other things. Okay? And we'll elaborate on those later. All right, so I've just added a covalent bond summary. Okay? And it's in some ways to give you a little review guide, but I want to show you another little learning technique. What I do is I break up the PowerPoint lectures into concepts, concept 1, 2, 3, and 4, and give each a title. What I recommend you do, all right, is organize each chapter or topic by the concepts that I give you, and then write your own concept summary for that concept. Write your own. I can write them for you, but they are not nearly as useful to you as you writing them yourselves. When you write them yourselves, first, you've got to go back and review the material. That's really important to your learning. If you don't write them yourselves, you don't go back and review it. Second, if you don't write them yourselves, you don't go back and review it. That's number 1 again, but it's an important one, right? You've got to go back and review the material. If you get summaries, what you tend to do is read those and read those only and not look back at the material. That gives you only a partial understanding. Go back, review the material. When you review it, you've got to understand it, all right? That helps you figure out some misunderstandings and misconceptions you've got. Then by you generating the review, you've reviewed it yourself, you've understood it, you've figured out any things you don't understand or misconceptions, then you've got to articulate it in your own words. All of that takes an awful lot of mental processing and organization in your brain, which really helps solidify the concept. writing your own summaries and study guides, I can't tell you how important that is. I know students love instructors to do it. It's because it takes you less time. It is not nearly as useful for your learning. Now, sometimes you don't do a great job on the review, and that's where instructor reviews obviously can help, because usually we hopefully get the content right and are usually complete. But I want you to move in the direction of sort of taking ownership over your own learning and writing your own summaries and reviews. They are really, really useful to you, and you'll get good at doing them and you'll get quick at doing them. All right, it could be something as basic and simple as this. Now, I wouldn't leave it as simple as this. I'd elaborate. So covalent bond review. Again, don't write this down. This will be on, you can write it down. I shouldn't say don't, you can. But it's posted on the PowerPoints. Atoms share electrons to fill valence shells. That's the crux of a covalent bond, right? Electron sharing to fill valence shells. You've got non-polar covalent bonds. That's between atoms of similar or the same electronegativities, and the electrons are shared right in the middle. And then you've got polar covalent bonds between atoms of dissimilar electronegativities. And then electrons, they shift one way or the other along the covalent bond depending on negativities, and that usually gives the molecule then some fairly unique properties. All right, they're important biologically. I think when you do your summary notes, it's really important to jot down little diagrams and sketches, really simple ones, because your brain, this is the way your brain works, you're very good at remembering and understanding and capturing images, but much less so with words. Okay? All right. Now we're going to move on to a second kind of chemical bond, ionic bonds. Right. So, here's the crux of an ionic bond. One atom transfers one or more of its outer shell electrons to another atom, which then uses those electrons to fill its outer shell. So one atom will transfer one or two, occasionally three, outer shell electrons to another atom that gladly receives them, and by receiving one or two and sometimes three electrons, it will fill its outer shell. Okay? So what's the, I guess if you were to use one word to describe a difference between a covalent and ionic bond, what would the one word be to describe ionic bonds? Non-sharing or transfer. Covalent bonds are sharing. Ionic bonds are transfer. Okay. All right. Now, when an atom loses electrons, there becomes a charge imbalance. All of a sudden, it has more protons than electrons, and it then becomes what we call an ion. An ion is simply a charged particle. It's where an atom either loses or gains electrons. In this case, if it loses electrons, it's going to have more protons than electrons, and it will have a positive charge. And we call that positively charged ion. Good? Conversely, what kind of ion would you be if you gained electrons? You'd be a negatively charged ion, because you've got more electrons than protons, so that gives you an overall negative charge. Okay? So we can have positively charged ions and negatively charged ions. Now, ions of opposite charges, in other words, a positively charged ion and a negatively charged ion, they attract each other. Opposite charges attract. And that then forms an ionic bond. Ionic bond is basically a charge attraction between two oppositely charged ions. All right, and then we'll look at an example to illustrate that concept. But is everybody okay conceptually with those points? Okay. All right, so what I want to do then is draw an atom that loses its electron or electrons to become an ion. Let's take a really simple one like lithium. Atomic number 3. So in its nucleus, it's got how many protons?
Wait, which one?
Lithium, atomic number 3.
So it has
How many protons? 3. So it's got 3 positively charged protons in its nucleus. Let's not worry about the neutrons. All right, if we drew the electron configuration, we're going to have an electron there and an electron there in the first shell and a single lone electron in that outer shell. Okay, 1, 2, 3 negative charges, 1, 2, 3 positive charges. This is a lithium atom, and overall it's neutral in charge. Okay? Now, sometimes lithium will lose that electron. It doesn't cease to exist. It doesn't zap from existence. All right? Matter doesn't get destroyed in that way. It just loses it. So, when it loses it, let's say here we've got a lone electron. And then here's what was a lithium atom. 3 positive charges. It's only left with 2 negative ones. What's the overall charge on this ion now?
positive.
Positive 1 plus 1. Okay. Good. All right, what happens if we were to look at the next one on the periodic table is Be beryllium. Atomic number 4. How many protons?
4.
How many electrons? Now, beryllium can lose its outer shell electrons. So let's just eliminate them. Gone.
Both of them?
Both of them. Because they lose electrons until their outermost shell is full. By losing those 2, that shell is gone, right? Gone, doesn't exist anymore. So this becomes the outermost shell, and it's full. Good?
What do you mean by losing them? Like,
Keep them away.
They can be lost.
like to another atom? Like to another atom?
Give me that water bottle. You don't know where it is, you just lost it. It's no longer yours. It's no longer in your arena. It's kind of the same thing.
You, yeah.
Sorry? Yeah, but imagine you didn't see me take it. All right? The guy behind you just pickpocketed you. Your wallet's gone. You just lost it. Gone. Nowhere near you.
So they just like can be zapped away?
Well, something takes them. Okay? I'll show that in a second, but we can have an atom over here, which is the one that takes them.
Okay.
Okay? So, if that atom takes them, so don't worry for right now where they go. We'll show you where they
But
go.
something is taking them away.
Yep.
Okay, they don't just leave.
You know, they can just leave, yeah. If you give them enough energy, they can just leave. All right, and then we can ionize beryllium. So if it loses those 2 electrons, yeah, that shell is gone. It's a bit like, you know what a queue is, don't you? You call it a line. You're at a cash register, right? If all the people are gone, is the queue left? Is there a queue anymore? There's not, is there? If all the electrons are gone, there's no shell anymore. It's gone. Okay? So this becomes its outer shell now. And it's full with 2 electrons. But now we've got 4 protons and only 2 electrons. So what charge will this ion be? 2 plus. We can write that like that. Or we can say 2 plus. Good? All right.
Because, wait, why is it 2 plus?
Because we're saying this ion has 2 positive charges to it.
Okay.
Because we've got 4 there, 4 positives, 2 negatives. The 2 negatives balance out 2 of those positives, and there's 2 left over. Okay? All right. So let's have a look at this then with a slightly more complicated atom. Let's look at this with sodium. So here we've got a sodium atom. It's all good. Everybody comfortable with that? Electrons are arranged nicely in those shells, right? Sodium's got an atomic number of 11. We can count up the 11 electrons, and it's got 11 protons. And there's chlorine. Chlorine's got an atomic number of 17. It's got 17 protons, 17 electrons, which we can count. Now, when an atom of sodium and chlorine collide or come close to each other, chlorine, being extremely electronegative, exerts an attraction on that lone outer electron. Sodium is not very electronegative. Sodium can barely hold on to that electron, so chlorine takes it. So that's where it goes in this case. Comfortable with that?
Yeah.
Okay, gone. So sodium no longer has it. Chlorine has that electron. So
it
let's...
has to go to an atom that has a higher electron negativity.
In the case of an ionic bond, yes. That's the reason why it gets taken, is that high electronegativity. So let's look at sodium. It's got an atomic number of, oh, what was it again?
Wait, sodium?
Atomic number of 11. So it's got 11 positively charged protons and 11 negatively charged electrons. That gives us a neutral atom. Okay? If it loses an electron, then we've only got 10 electrons, 11 protons. Now we've got a surplus of 1 proton. So the sodium becomes a 1+ ion. Good? Now, when sodium loses that electron, this is now its outer shell. That outer shell is full. Okay? Chlorine, when it receives that electron, chlorine's got an atomic number of 17. So that means it's got 17 protons, 17 electrons. When it gains an electron, it's got 18. And now we've got one more electron than protons. So chlorine then has a 1 negative charge to it. Good? All right, so we've just transformed that atom into a chlorine ion. We've transformed the sodium into a sodium ion. Now, when chlorine receives that electron, its outer shell is full with 8. Good? All right. So, sodium transfers its outer electron to chlorine. When it does that, it's got a full valence shell. As a result of transferring it to chlorine, chlorine has got a full valence shell. They've both got full valence shells. Remember, whenever we're talking about chemical bonds, covalent and ionic bonds, the end result is a full outer shell, a full valence shell. All right? And then it looks like this. We've got a sodium ion with a 1+ charge, a chloride ion with a 1 negative charge. That positively charged ion is strongly attracted to that negatively charged ion, and that attraction is an ionic bond. Okay? Good? Okay. We don't represent ionic bonds with a line. What are the only bonds we represent with a line between the two atoms?
Covalent.
Covalent bond. Ionic bonds we don't represent with a line. Compounds that are formed by ionic bonds form substances we call salts. Now, I know you're familiar with salt, right? Table salt. Table salt is sodium chloride. But substances that result from ionic bonds, in fact, not all of them that have ionic bonds are salts. But if they involve things like sodium and lithium and potassium and calcium and chlorine and iodine and fluorine, if they are between those first two columns in the periodic table, elements, and the column with oxygen and the column with fluorine, those are all salts. Okay? Good? we just call those substances salts. But through common use, we've used the word salt to refer to sodium chloride. But we could have magnesium chloride. That's a salt. Okay? It's just a substance formed by ionic bonds. Yeah.
Do these elements bond if they're just like poured together, or does something have to happen for them to like bond?
They've got to come in close proximity to each other. So you've literally got to get a sodium atom come in close proximity to a chlorine atom.
But as long as they come,
That's it.
It'll form.
That's exactly it, yeah. Do you remember what chlorine looked like? It's a green gas, yeah? Remember what sodium looked like? It was that silvery metallic metal. Chuck some of that sodium in that flask of chlorine, and the reaction is incredibly violent. It will probably explode. But that's all you've got to do. Put them next to each other.
And that'll just make salt.
Yeah, it will. It will make sodium chloride. Yep. Isn't that crazy? You'll get white crystals form. We should try it. I'm all over that. Do you have a question? Nope. Okay. All right. But that's not true for everything. Think about hydrogen and oxygen. Yep. When hydrogen and oxygen combine together, they make what? They can make water, right? Or water. I don't know. However you want to say it. Okay? So they make water. But I could mix hydrogen and oxygen together, and they won't combine. They'll stay as a hydrogen molecule and an oxygen molecule. In order to get chemical reactions going, in other words, in order to start them sometimes, we need to add a little bit of energy. It just depends on the elements involved. In the case of sodium and chlorine, they're so reactive themselves, it just kind of spontaneously happens with the amount of energy in the environment. With something like hydrogen and oxygen, we need to add energy into the system. In other words, a spark or a flame adds enough energy to get the reaction going. Then hydrogen and oxygen will combine. Okay? And it will keep going. We'll talk more about that. It's called activation energy. All right. Good? All right. So we're going to watch this little animation. It really helps understand ionic bonds.
Or giving away electrons. This happens between sodium and chlorine atoms. Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons, but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case, a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Good, does that help? I think it does. Just the fact that that electron moves over helps visualize that. All right, so let's take some sodium chloride. It's a crystalline substance, and there we can see the organization, the arrangement of the sodium ions and the chloride ions in that substance, in table salt. Good? Very nicely, regularly arranged. All right. Any questions about ionic bonds then before we move on to hydrogen bonds? Good? Okay. So hydrogen bonds then, we sometimes abbreviate it to H bonds, hydrogen bonds, H bonds. All right, this is a little bit of a wordy definition, but we'll give you the definition and then sort of break it down bit by bit. So a hydrogen bond then is formed by a charge attraction. That means you've got opposite charges that are attracted to each other. So it's a charge attraction between a hydrogen atom, so a hydrogen bond always involves a hydrogen atom. And that hydrogen atom is always covalently bonded to some other electronegative atom. So the hydrogen bond is between the hydrogen that's bonded to a highly electronegative atom and another electronegative atom. So I'll diagram that. Again, I think these little sketches and diagrams massively help explain. So let's break down this definition. Here we've got our hydrogen. And that hydrogen is covalently bonded to a highly electronegative atom. So give me an example of an electronegative atom that this hydrogen could be bonded to.
Oxygen.
Yeah, oxygen. Honestly, there's usually 3 or 4 main candidates. All right, fluorine, chlorine, oxygen, and nitrogen. So let's just say it's bonded to an oxygen. There. Covalent bond between hydrogen and another highly electronegative atom. Now you know that's a polar covalent bond. What's the charge around the hydrogen? It's a little more positive, and we do that with that little symbol there. So the hydrogen bond itself is between this hydrogen and some other electronegative atom. Give me an example of an electronegative atom. Not oxygen, though, some other one. Maybe nitrogen. Nitrogen we know is electronegative. There's the nitrogen. Okay? Now, we don't draw it as a straight line because it's not a covalent bond. We typically draw it as a dotted or dashed line. So what's the charge around nitrogen?
It's going to be more negative.
More negative. Now let's just complete this. Oxygen, because it forms 2 bonds, there's a covalent bond there to something else. Yeah? I don't really care what it is right now. It could be a lot of different things. So I'm just going to write this generic letter R to say the remainder of the molecule, the rest of the molecule. Okay? It could be anything. It could be another hydrogen, or it could be something much more complicated. And again, with the nitrogen, how many more bonds does nitrogen form? 3 covalent bonds, right? 1, 2, 3. All right. So again, I'm going to collectively write R, the rest, the remainder, something else. We don't really care right now. This then is the hydrogen bond.
And that's why you do it with a dashed line.
Because it's not a covalent bond. Right, it's just showing there's a charge attraction. Everybody okay with that so far? Again, I'm going to elaborate on that, but it's really important you understand hydrogen bonding. I'm going to be talking about it an awful lot throughout the semester. So let's sort of phrase it in a slightly different way. When hydrogen is covalently bonded to oxygen or nitrogen, both oxygen and nitrogen are highly electronegative, right? That results in polarity across that bond. We're going to have a positively side by the hydrogen and a slightly negative side by the nitrogen or the oxygen. So the negative side can be attracted to another molecule. The positive side, the negative side to another molecule. And in this case, the positive side can be attracted to the negative side of another molecule, or this negative side can be attracted to the positive side of another molecule. Good? No?
Wait, so when does the hydrogen bond come in?
This is the hydrogen bond. It's the attraction between this positively charged side of the molecule and this negatively charged side of the molecule.
And what's the difference between the other covalent bond?
Here we got hydrogen, here we got hydrogen. In this case, it's bonded to oxygen. In this case, it's bonded to nitrogen. Both nitrogen and oxygen are highly electronegative. As a result, the electrons shift over to here. So this is the positively charged side to the molecule, and this is the negatively charged side to the molecule. Okay? Now, in this case, this positively charged side to the molecule will be attracted to the negatively charged side of any other molecule that's around. That attraction is the hydrogen bond because it joins these two together. Okay? If this is, I know you're giving a nod, but
So
you
is
really
that like
mean,
more-
I can see it in your eyes, it's like,
So one of them is non-polar, one of them is polar, but they're still covalent. Is that what it is?
no, this is a polar bond, that's a polar bond.
Oh, okay.
It's just a hydrogen bond.
But like, so why would it want to gain further?
It's not gaining anything. Let me draw a water molecule for you. There's an oxygen. Again, you've got to understand polar covalent bonds. If you don't, you're going to be lost with hydrogen bonding completely. There's a water molecule. One covalent bond, another covalent bond. This is a highly electronegative atom. It's going to make all the electrons spend more time over here. Electrons are negatively charged, so this is the negatively charged side to the molecule. This is positively charged. Now, this did not lose an electron. There's no transfer of electrons here. There's no transfer of electrons here. It's just that they've shifted over here. So there's a cloud of negatively charged electrons there, which makes this a negatively charged side to the molecule. Over here, there's very few electrons. So we've got the positive charge of the proton in the nucleus, making this side more positively charged, more positively charged. Okay? Now, water molecules don't exist by themselves. They exist with lots of other molecules, maybe other water molecules. So if I've got another water molecule here, the same thing exists, negative, negative, positive, positive. Now, what's going to happen when these two come close to each other? This positive charge is going to be attracted to what? This negative charge. Opposite charges attract. If this hydrogen kind of bumps into this, it's going to be repelled by it a little bit. Now, when they get close enough, these charges really attract. And that's a hydrogen bond. Okay? Hydrogen bonds aren't permanent. They're made and broken all the time. New ones make, new ones break all the time. They might only last for a fraction of a second.
So it's between different molecules, it's not between different atoms?
It is between different atoms,
Oh,
but those atoms are not part of the same molecule.
okay, so they have to be covalently bonded to another atom.
Yes,
Okay.
but here's where it gets, again, a little, not complicated, but there's no hard and fast rule. This hydrogen bond could form between a hydrogen and an oxygen that are in the same molecule. Some molecules are huge, and there's a hydrogen over here and an oxygen over here, and they can hydrogen bond. In this case, it has to be between two molecules, but it doesn't have to be between two molecules. It can be between different parts of the same molecule. You had a question at the back?
Yeah, so there's not electrons being shared, right? Between the hydrogen.
With a hydrogen bond, there is no sharing and no transfer of electrons, right? Sharing of electrons occurs only when? Good, covalent bonds. Transfer occurs only when? Good. Hydrogen bonding is just a charge attraction. Okay? Okay. All right. So here's a diagram that represents hydrogen bonding between a water molecule and a molecule of ammonia. Ammonia is NH3. Nitrogen with 3 hydrogens covalently bonded. How can you recognize this as a hydrogen bond? There is a lot of clues in this diagram.
The dots.
Dotted line. Honestly, that's, I guess, the least important way that I want you to recognize a hydrogen bond. But it's a really obvious one, isn't it? What would you, why would you look at this and say, oh, there's got to be a hydrogen bond there? No, beside the dots. Let me say I erase those dots. Why would you say, oh, there should be a hydrogen bond there?
Because the hydrogen, and then it's positively charged, and the nitrogen is negatively charged.
First, there's hydrogen involved. Second, you can see that hydrogen, in this case, is covalently bonded to an oxygen. That instantly tells you this is a polar bond, and it's water anyway, so you should know that about water. Ammonia. Maybe you don't know anything at all about ammonia.
Very, very toxic.
Well, it's very reactive, right? It can be very toxic because it's so reactive. So what you do know is nitrogen is very highly electronegative, and it's covalently bonded to hydrogen. So you should be able to work out or deduce or surmise that this is a polar covalent bond. I might ask you a question in an exam where I give you a molecule you've never ever seen. But if you know the electronegativities of the atoms involved, you should be able to say, all right, that's a polar covalent bond. And as a result, there's going to be a negative side and there's going to be a positive side. And as a result of this being a negative side, this being a positive side, they're going to attract. And that attraction is a hydrogen bond because hydrogen's involved. Okay? All right. Think you could do that if I gave you some mystery molecule you've never seen before? Good. Now, hydrogen bonding in water gives water some really unique properties. One property that it imparts on water is that water has high surface tension. Even though steel should sink in water because it's more dense, take something that's fairly light, like a paperclip, and you can very gently float it on the surface of water. Think about it. If every water molecule is hydrogen bonded to every other water molecule, it's a bit like, imagine I'm a water molecule and you're another water molecule. It's a bit like this. They're constantly doing this, and then this, and then this, right? So it's a bit constant up. Certain molecules are joined, and they're going to hold something on top of it. Now, if I have an elephant jump off the stage, people are not going to hold it up. There's a limit to what that hydrogen bonding can do with respect to surface tension, but make it light enough and it can hold it up. It also allows water to remain liquid over a very wide range of temperatures. If here's a beaker and it's filled with water, think about every one of those water molecules. I'm just going to draw each molecule as a dot. There's some hydrogen bonding between them. In order for the liquid to be converted into a gas, in order for the liquid to boil, these water molecules have got to break all of their hydrogen bonds and leave the liquid, go into a gaseous state. All right? Those hydrogen bonds, to break a lot of them, takes a lot of energy. It's why it takes a lot of energy to boil water, and it's why it's liquid over a very wide range of temperatures. Okay. All right. Now, hydrogen bonds are fairly weak. They're about 5% the strength of a covalent bond. But many, many hydrogen bonds together, they can be strong. So even though individually they're weak, collectively they can be quite strong. All right. Are you comfortable with hydrogen bonds?
Yeah.
Think so? Yep. questions? Good. All right. So now we're going to move on to our fourth biologically important bond, and that is van der Waal forces or van der Waal interactions. Who do you think these were named after?
Someone, Mr. Van der Waal.
Yeah, I would imagine Mr. or Dr. van der Waal. So, electrons may not be equally distributed in a molecule. They might be unevenly distributed in a molecule. Sometimes, just by chance, they can accumulate in one side of the molecule compared to the other. So I'll give you an example. Here's a molecule. Okay, there's a molecule. Now remember, electrons, I know I've said they exist as shells, but that's more sort of as a concept. Electrons exist as clouds, don't they? Yeah, there's clouds of electrons. And obviously there's clouds of electrons around the hydrogens, and there's clouds of electrons around the carbons. But the electrons can kind of move around within the molecule. So sometimes the electron cloud might go to one side. And if the electron cloud quickly drifts to one side, let's say the electron cloud drifts over here, what charge is this end of the molecule going to have? Negative. Now, we don't really put a symbol. We don't do this, because it's not really a permanent thing. But if the electrons drift over here, that's going to be the negative side. If they drift back over here, that's going to be the negative side. If they drift over here, that's going to be the negative side. And then other parts of the molecule might be the positive side. Do you see how that can happen? Yep. It's a bit like this. Imagine we were on a boat in a very rough ocean. The boat's doing this. You're going to go, oh, all the way over that side. And then, oh, maybe all the way over that side. Electrons are kind of like that. They're drifting by chance, just in different places. And that's going to make one side of the molecule more negatively charged than others. Well, of course, this might be next to another molecule, exactly the same. So just imagine all the electrons sort of drifted over there, and these electrons happen to drift over this side. Well, then there's going to be a little attraction between these two sides of the molecule, yeah? But as soon as the electrons drift back, that attraction goes. But then maybe this is the negative side, or positive side, and it might be attracted to a neighbouring molecule. These electron clouds are constantly shifting. So can you see how these van der Waal attractions are going to be constantly changing, but they're always going to be present. Okay? Yeah.
But they're not actually like transferred or shared between the two. They're just kind of
Correct.
moving.
No transferring or sharing. Again, it's just like you're on a boat that's doing this, you're not jumping off, and you're not being shared. You are on your boat. You're just shifting around within that boat. Okay? What's the only time there's sharing of electrons? The only bond type. And the only time there's transfer of electrons? Ionic bonds. Good. All right, so one end of the molecule might become charged, and opposite charges attract, and that's what a van der Waal interaction is.
So
Attractions.
it's just an attraction, but there's no actual, like...
Yeah, it's a very weak, very transient attraction.
Okay.
Now we're attracted, now we're not. Now we're attracted, now we're not. Now we're attracted, now we're not.
You know?
Sorry?
So it's kind of like junior high dating.
Yes, exactly what it is. Junior high dating. That's a good analogy. But there can be lots and lots and lots and lots and lots of them. And so collectively, they can be quite strong. They all add up. Think about a rope. A rope is made of tiny little individual fibers. Each fiber itself is weak, but put them all together into a rope, very strong. That's what happens with these van der Waal forces, or these van der Waal interactions. Now think about a gecko. You can think about the Geico gecko if you want. Think about a gecko. Geckos are really good at walking up vertical surfaces with their feet. And there's a couple of different reasons to that. But one is that it just so happens that the surface of their feet has a huge surface area, and it's got a chemical composition, which means there are many, 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 many van der Waal forces. And the surfaces that it can walk up also have many, 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 many van der Waal interactions. And so a gecko is literally able to stick to the things it walks up by van der Waal attractions between molecules in its feet and molecules in the surface it walks up. Isn't that cool? So there's a gecko. And when you have a look at the feet and pads of a gecko, firstly, they're kind of spread. They're sort of like sucker-like. But their ability to attach to a surface is not because of suction. All right? Big surface area, lots and lots and lots of folding. But now look at this next image. So this is a scanning electron micrograph of the foot of a gecko. Huge surface area. On an uneven surface, those hairs are going to sort of come in contact with every part of it. And there's a scale bar, 100 micrometers, 1/10 of a millimeter. And the chemical composition means there's lots and lots of van der Waal forces. And they've actually constructed an adhesive that's mirrored after gecko feet. And it's extremely strong. It's called gecko skin. Small pads of it stick to surfaces, but it's not glue, it's not sticky. It sticks because of van der Waal forces, and it can hold enormous weights. Go online and you'll see videos of people that have, it's a bit like Spider-Man, I'll tell you in reality. There's a climber, and he's got a little pad, not a suction cup of this stuff, and on his feet, and he climbs up a glass wall as a result of the van der Waal forces sticking into it. Isn't that cool? So that just shows you that collectively they can be quite strong, but individually they're weak. All right. So that's our chemical bonding concept. Any questions about chemical bonds before we move on? We are going to be talking an awful lot about chemical bonds throughout the semester. Yeah, question.
How would you show an ionic bond?
How would I show it?
Yeah.
With an ionic bond, we don't use a line. Here's what we typically do, is we'll show the ions. See that charge? And we'll just know, well, this is positive charge, that's negatively charged, they're attracted to each other. Okay? And again, with ionic bonds, when they form a compound, think about all the crystals of a salt. Yeah? All the crystals in just table salt. And then think about that diagram I showed where you've got alternating chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium. So they exist as this sort of crystalline arrangement of atoms. Whereas this substance, which is held together with covalent bonds, this is its own molecule, separate to this molecule. Yeah? It's kind of hard to separate a sodium and chlorine into a molecule. It doesn't really exist like that. Does that make sense? No line. All right. Good? Concept 6, ready? So concept 6 is about molecular shape and function, and how shape and function are related at the molecular level. So remember, the molecular shape is super important in biology because it determines how the molecule functions. Its shape does. So its shape determines its function. And the shape of a molecule is really important, critically important, as to how one molecule recognizes and responds to another molecule. Shape and function are interrelated. The shape of the molecule determines its function. So at a very, I guess, simplistic level, if I've got a molecule, and I'm going to make up a shape, and a molecule is shaped like this. Just say I've got a triangular shaped molecule. Its function is related to its structure. So as long as the molecule has that shape, it will perform its function. Okay? But let's just say I do something to change the shape of the molecule. Maybe I change it to something like that. I just chop off each corner. That's a pretty drastic shape. But by changing the shape of the molecule from that to that, I've now probably just changed its function. Is everyone okay with that? So many times with biological molecules, they'll have a shape, and there will be another molecule which is maybe a receptor molecule, which this fits in. So if we've got this molecule as this shape, and let's just say we've got a receptor molecule that might be that shape. Well, that perfectly fits in there. And when this perfectly fits, maybe that then triggers its function. Does that make sense? I'm being very generic and general, but I'm saying, you know what, we've got some molecules that are able to fit a molecule within, like a jigsaw piece, right? If I change the shape of this, it will not fit in this anymore, and so it may not have its function. Its function may be lost. Okay? Now, those of you that are into origami, just imagine I change this shape because I simply folded this over there like this. Folded it. So I can take a molecule, fold it slightly differently, doesn't fit, its function's gone. But then if I fold it back, it does fit, function's back. So I can literally turn molecules on and off, at least functionally, by changing their shape. Yeah? Okay.
So nothing ever leaves, it just gets moved?
It can, totally. Maybe it moves, or maybe I've got this, that piece. Sometimes these two join together, sometimes this leaves. Both happen. Okay? But the main point is that the structure or the shape of the molecule is very important for its function. Change the shape or structure, you very often change its function. Okay? All right, so let's have a look at these molecules then. This is a slightly different way of diagramming a molecule. All right? You can see that everything in black is a carbon atom. Everything in, what is this color? Is that white? It's white or a light grey, isn't it? Light grey. They're the hydrogens. Hydrogen is usually depicted in white. Blue is nitrogen, which is usually shown in blue. Yellow is usually sulfur, and red is usually oxygen. So let's have a look at this substance over here. You can see every one of those grey or whitish grey spheres is a hydrogen atom. Each one of these little wedges is a carbon atom, and each of the red ones is an oxygen atom. This is the structure. Oh, there's a little nitrogen tucked away in there. This is what a morphine molecule looks like. Morphine's an opiate. Yeah? Sorry?
No, I just said I am very strong.
Yeah. So it's got very, very strong pain-killing properties, right? You know that already, don't you? Yeah. All right, so there's morphine. And now we've got this is the molecular shape of an endorphin. Endorphins you naturally produce inside your body, right? In fact, endorphin is short for endogenous, which means internally produced, morphine. Endorphin, endogenous produced morphine. All right? Now, morphine is produced by what? Plants. Certain plants produce morphine. Okay? In fact, we've found, I think recently, I think this is accurate, that certain parts of your brain can actually produce morphine as well. Certain chemicals, certain tissues in your body can also produce morphine. But let's not worry about that right now. Plants produce morphine. You produce endorphin. All right? Endorphins are also responsible for dulling or killing pain. Okay? Morphine is responsible for dulling and killing pain. Now look at the shape of this part of the endorphin molecule. See, we've got a hydrogen and oxygen, and then those 6 carbons, and 1, 2, 3, 4 hydrogens. Now look at this one. It's almost the same, isn't it? There we've got the hydrogen, oxygen, 6 carbons, hydrogen, hydrogen. There we've got an oxygen, slightly different. So they're very, very similar, the shape here and the shape here, aren't they? The fact that they have very similar shapes, we would predict they would have similar functions. Okay? And they do. Morphine fits a receptor molecule because of its shape. There's a receptor molecule, like a jigsaw piece, that can receive endorphins, that part of it. And when it does, when the endorphin locks into the receptor molecule, the cell that molecule's in, no pain. Morphine fits a receptor molecule because of its shape. So you have receptor molecules that fit endorphins. Morphine will fit it also because of the similar shape. That's why they have similar effects. Does that make sense? Okay. So here's a brain cell, a neuron. This is the cell membrane. This is inside the cell. This is outside the cell. And here's a receptor molecule. In this case, it's called an endorphin receptor that sits in the membrane. When endorphin is produced, it locks in. That part fits. And it sends a signal to the cell, no pain. Just by chance, by coincidence and chance alone, plants produce a chemical, morphine, that also fits. And it has the same effect. It says no pain. In fact, it might not be by completely random chance that it's the same shape. There's probably other reasons for it. Good? Okay. All right, we're going to talk quite a lot in later chapters about the shape of the molecule being responsible to its function, and then what happens when we change the shape of the molecule, what happens to its function. All right, so concept 7 then is chemical reactions. We're going to look at chemical reactions, how elements and compounds undergo chemical reactions to form new substances. So chemical reactions then, it's the process of making and breaking chemical bonds. Chemical reactions involve breaking some bonds and making new bonds. In fact, chemical reactions is the ultimate form of recycling. Nothing's wasted, everything's used. We tear apart one thing and build up something else. Now, in a chemical reaction, the molecules you start with, the substances you start with before you start to break the bonds and break them apart, are called the reactants. And the ending molecules, the ones that you build back up by making new chemical bonds, they're called the products. So chemical reactions have got reactants and products. And because it's this ultimate form of recycling, everything is used and everything must be accounted for. We can't destroy matter and we can't make new matter. Everything must be accounted for and nothing gets destroyed. Okay? All right. Are you okay in concept then? What a chemical reaction was? We'll look at a bunch of examples so you can see how we start with reactants, break the bonds to tear them apart, and then how they build back up into products by making new bonds. So, here we've got one hydrogen molecule. There's a hydrogen atom, covalently bonded to another hydrogen atom. There's another hydrogen molecule, a hydrogen atom, covalently bonded to another hydrogen atom. And here's an oxygen molecule, one oxygen atom with a double covalent bond to another oxygen atom. Okay? Now we can represent this oxygen atom as O2, or we can represent it like this. We can represent these two hydrogen molecules like this. Two hydrogen molecules. Is everybody okay and comfortable with that? There's an oxygen molecule. It says two oxygen atoms. Here's a hydrogen molecule. It says two hydrogen atoms. Now, if I've got two hydrogen molecules, I've got two of these. Yep. If I had three oxygen molecules, what would I put in front of this? Three. Okay? All right. So in this case, then, we've got two hydrogen molecules. Now what we have to do is we're going to react hydrogen with oxygen. Now when we just mix hydrogen and oxygen together, we can shake it together in a flask. They're not going to react together. We've got to actually input some energy. All right? We're going to input some energy, maybe in the form of heat. And what we're going to do then is we're going to break the hydrogen atoms apart in the molecule. Okay? So here we've got two hydrogen molecules. Here we've got one oxygen molecule. We're going to add some heat. And that's going to make, think about this, an oxygen and an oxygen and a hydrogen and a hydrogen and another hydrogen and another hydrogen. Now, I don't want you to think that these are just existing floating around by themselves. They're not. But a hydrogen molecule, if we add some energy, this bond can be broken. And then we've got these. These are very reactive and short-lived. The minute one of these gets close to an oxygen and that one gets close to an oxygen, zip, they bond together. So then that happens. That takes maybe these two into account. And then these two will make new bonds together to form another one. Good? See how that works? So here we've got our reactants. Add a little bit of energy to break the bonds. They'll join together to form new substances, in this case, two water molecules. There's an H2O. There's an H2O. We've got two H2O. Good? Very simple chemical reaction. Is everyone comfortable with that? Because we're going to go through a couple of examples. We're going to get progressively more sort of complicated. Good? All right. Okay, so let's have a look then at good old carbon dioxide. Carbon dioxide, CO2. So there's a diagram of a carbon dioxide molecule. It's one carbon, two oxygens, double bond between them. How do we get carbon dioxide? What are the reactants for producing carbon dioxide? What do you think the reactants are?
Carbon and oxygen.
How about carbon and oxygen?
Maybe.
Maybe. Let's say it is carbon and oxygen. Yep. Good. So to get carbon dioxide, we've got to have some carbon that we're going to combine with some oxygen. Good? All right. One carbon atom combined with one oxygen molecule gives us one molecule of carbon dioxide. The reactants in this case are what? Carbon, oxygen, and the product is carbon dioxide. Okay? Now look at the ratio. Carbon dioxide is CO2. So for every one carbon, there are two oxygens. Good? Okay. Now let's look at methane. A bit more complicated. We've already encountered methane, haven't we? It's CH4. One carbon, four hydrogens. And that's what the molecule looks like as a stick diagram. That's what it looks like as electron configuration. So to get methane, what do you think the reactants are? What have we got to combine together to get methane? carbon, and hydrogen. Now, let's have a look at this one. We've got one carbon and we've got one hydrogen molecule to make CH4. We've got to have exactly the same of atoms in the reactants as we do the products. So how do we get 4 hydrogen atoms?
You must have started with
2 hydrogen molecules. Everyone okay with that? Can you see how in this 2 hydrogen molecules we get 4 hydrogen atoms? Good? And that's how they combine. So our product, of course, is methane. All right, going to give you a slightly more difficult one. You ready? Anybody know what this substance is?
I know there's
C2H5OH. A bit more complicated. How many carbons there? 2. How many hydrogens? 6. How many oxygens? 1. All right. That stuff is ethanol. Okay, it's ethanol. I know we always call it alcohol, but there are lots of different alcohols, ethanol being one of them, so it's ethanol. All right, now how do we make ethanol? What do you think we combine together? Carbon, hydrogen, oxygen. Yeah, we do. We combine carbon, hydrogen, oxygen together. Okay? So we're going to take some carbon, we're going to add it to some hydrogen, and then we're going to add that to some oxygen. But just the same as with methane, there's a bit of an imbalance, isn't there? So, for example, how many carbons do we have in the reactants right now? In the reactants right now. 1 carbon. How many have we got in the products? That's an imbalance. How many hydrogens have we got right now in the reactants? 2. How many have we got in the products? 6. How many oxygens in the reactants? 2. How many in the products? Now, what we've got... Don't say it if you know the answer. That was a light bulb moment, wasn't it? It's like the clouds parted, the angels started singing. All right. So, what we've got to do is, just as we did before, we've got to add some numbers to say, all right, well, we've got this number of molecules of hydrogen, maybe this number of molecules of oxygen. Now, we don't just change the number of molecules in the reactants to make the reaction balance. We can change the number in the products as well. This is homework for next time. Balance this chemical equation. Okay, write it down, balance it. The answer's in the PowerPoints, balance it before you look. There's also a link on Canvas. If balancing chemical equations is a little bit problematic for you, there's a link to a tutorial that gives you loads of practice at balancing chemical equations. Okay, it's a good tutorial. All right, everybody have a great weekend.